All right, guys, enjoy the lecture. See you later on. Hello, bye.
All right, guys, thank you for making it this awful morning. Driving down the M40 for half an hour this morning was not much fun, but fortunately there weren't many self-driving cars, which would be completely screwed up by the weather conditions. So, right, it is 5 past, so I will start. Something new today. So I won't do any review on the past lecture, because we are going to talk about image processing. Right, can we see that? Yes. Image processing. It's a preprocessor before we attempt to do recognition. And clearly, as humans, we are doing it. It involves normalizing as far as possible by algorithms that we know the data. So if I was trying to recognize one of you guys, I'm in this room, my eyes are taking a view of the whole room, and I am going to say focus or concentrate on one guy who I want to recognize. And as I get close to him, he dominates the image, and all the other guys fade away. And if you think of the human camera, i.e. the eyes, again is very different from the cameras you have on your phone. Because the cameras on your phone, they are taking in each individual pixel, and each pixel has the equal amount of information. If you look at the retina of the eye, all the cells are concentrated in the center of the eye, and they're tiny ones, and as they get outside, they're bigger. The resolution outside of the periphery is much lower than the resolution on the center. So we use physical motion, i.e. moving our eyes, or even moving our head, to normalize and focus on what we're doing. So if I want to recognize you guys, I wouldn't take a picture of the whole room, I would concentrate on one person, and I would capture that information, the center of the object, and separate it from the background. And the good news is we know most of the image processing operations we wish to do. Good evening. Is it wet outside? A little bit. Right. So, and also a lot of the functions, edge detection, filtering, they are using the same type of algorithm, this sigma I equals 1 to d of wi ii, which is the function of the neuron, the analog neuron. In the case of image processing, we actually know the weights. We know what we want to do. So really, this part of the course is easier. So, what's it all about? The first thing I want to look at, now stay there, is image enhancement. Now look at that image and tell me what you see. What's in that image? Can you recognize the guy in there? No. Well, by simply operating on the pixels with an algorithm, we can go from that image to that image. And that guy is hidden in the upper image. Okay, the resolution, the difference between the pixels is very, very small, beneath the resolution of our human eyes. So we can't resolve this. But if we do image processing operations on it, we get that out. And you most probably recognize the guy. I think he was an actor many years ago. I think it was Richard Burton. I could be wrong on that one. But clearly it's a guy. And I think you might be able to recognize him as a human from seeing that picture. So that's pretty smart, isn't it? How do we do it? Okay, let's start from first principles. And I want to give you a number of algorithms. A lot of them are simple and common sense, but there are certain conditions we have to apply which might not be obvious. So, single pixel operators. Now, in some books, these are called monadic operators. I don't know why they use an obscure word like that. Single pixel explains exactly what they are. Monadic operators are operating on single pixels. So if we take an image, it is going to be made up of pixels. In the real world, it's going to be millions of pixels. For the purposes of exams, to get the idea of the operators over, you will be seeing images of 4 by 4 pixels. The principle is the same. Within that image, there is a pixel, Aij. I is the row, column, and J is the row. And remember, the top is the origin. And that can be, the total thing can be called picture A. You extract information from that pixel, and you calculate a function of Aij, which outputs a pixel, which appears in the output image, and let's call the output image B. And it produces an image at exactly the same Aij location. So it's a single pixel operator. And of course, for real images, you have to do that for as many pixels as you have in the image. If it's on your phone camera or modern high resolution images, there could be 16 million operations to do. So image processing is quite computer intensive. If you go back 20 or 30 years, you couldn't do it on a computer in real time. You had to have special purpose hardware. But nowadays, image processing is quite trivial on the technology we've got. So, what can we do with monadic operators? And the first algorithm is image intensity shift. And the intensity shift is the output pixel, Bij, and I'll use the notation in these. There are papers on Blackboard which gives this. Bij equals Aij plus K. And it is essentially an add operation. And it can be regarded as a brightness control. So, we are, sorry, K, make that K. Right, that's relatively straightforward. You are adding a constant to the pixel, and if that constant is positive, it will increase the intensity. If K is negative, it will reduce the intensity. But all images systems are fixed point resolution. If it's color, it's 24 bits, 8 bits for red, 8 green, 8 blue. If it's gray, it's just 8 bits. And that's going to be a range of 0 to 255. And by taking a pixel, Aij, and adding a number to it, it could go outside the range. So you've got 8 bits, go for the case of a gray image, you've got 8 bits available, you've got the starting off with 250, and you're adding a K of 10 to it, it gives you 260. 260 is beyond the resolution. What are you going to do? Well, you could take the least 8 significant bits, and I think 260 would be, well, let's do it out. Well, let's go to 5 bits, to 4 bits, it's easier. Supposing I had 14 plus 3. In binary, that would be 8, 12, 14 plus 3 would give us 17, which is 1, 0, 0, 0, 1. Now, if I were to take the 4 bits, which is the resolution of the input, I would have that. And that would be a very low value. That would take the pixel to pretty well black. If I took the most significant bits, it would be value 8, it would be somewhere in the middle. It would be a distortion. So you don't do either of those. If the intensity is greater than the resolution, the pixel becomes white, W. And that is for A, I, J is plus K is greater than or equal to W. And of course, going the negative way around, we want to clamp at the bottom end. So if the constant is negative, it takes the updated pixel to a negative value, it becomes 0, which is black. And that is for A, I, J plus K is less than or equal to 0. So we're actually clamping it within the top and bottom range after the shift. Right, that's intensity shift. There is also intensity multiply. And intensity multiply is equivalent to contrast.
Can you show the last sheet again?
Yeah, sure. Basically, if the addition is within the range, which is 0 to W, remember W is maximum white. And that in 255, 8-bit resolution would be 255, 4-bit resolution would be 15. And 0 is black, max black. Right. Intensity multiply. Can I go on? Right. Intensity multiply. Similar idea. Single pixel operation. The output pixel Bij is equal to Aij times K, a multiplication constant, which is variable depending on the change you want, the amount of change you want to do. And that will be true for Aij times K greater than or equal, less than or equal to W, greater than or equal to 0. If, however, we go to the limits, it becomes W. If Aij times K is greater than W, and it becomes 0 if Aij times K is less than 0. And that really is just a tidying up. That the last case won't really happen, because if you have a negative multiplication constant, it doesn't matter what the image is, the output will go to black. So that's just a safeguard in case a mechanical engineer is using your software and tries to do a negative multiply, which would be stupid. Okay, so that's the multiply. Threshold. And this is a band threshold. Why do we need threshold? Well, you've seen the digital neural networks, they need binary inputs. So real world is analog. We may need to have a threshold to get the information into a binary form. And here it is Bij equals maximum white, W, where Aij is within a band less than K2 and greater than K1. So we're taking a range of pixels between K1 and K2. They will cause the output pixel to be 1 or white. Outside that range, either below or above, the pixel will become black. So that is a thresholding operation. If it's not in the range, it's 0. Now the simple threshold is where K2 is equal to W. And Bij equals W if Aij is greater than K1, else 0. And that's a more common threshold. Set the threshold at K1, anything above that is 1, anything below that is 0. Right. So with these 3 operations, well, the first 2 are the most important, we can start thinking about image enhancement, do something really useful. So, can I move on? And this is improving the quality of the image. And this could be for human consumption. If you're operating closed circuit TV, it's taking pictures of a campus. What goes on, which shouldn't go on, is normally in the dark regions, not in the full light of the street lights or the floodlighting we've got. So you want to process and enhance what's going on in the shadows to see who is doing what, where, and when, if you're that way inclined. And quite interesting, on CCTV, it's quite often black and white images you're dealing with, rather than colour. Because if you start enhancing colour images by moving, shift, and add, you are changing the colour mix. And so the colours will actually change. And RGB is not suitable for colour enhancement. If you go to another colour representation, which is hue, saturation, and intensity, each getting 8 bits, if you go to the intensity, you can then enhance the colour images. But most computer images are RGB rather than HSI. So, let us take a grey little image. And the image, it doesn't have to be this one, but this one will do, for example. You can use different values if you like. It's the method rather than the answer that's important. And I am going to use a 4 by 4 bit image. The sort of resolution you might get in exam questions. There's dirt in the eye there. 4 bits in exam questions. Got it? Or he's all asleep. Right, and supposing the image values 4 bits rather than 16, to keep it easy. Let's take values 3, 4, 4, 5, 4, 5, 6, 5, 5, 6, 7, 6, 6, 7, 9, 8. Doesn't have to be those values, they'll do for an example. Right. What does that image look like? Can anybody describe what the image might look like? Remember, for 4 bits, 0 is max black, and 15 is max white. And you've got all the grey levels in between. Any suggestions of the appearance of that image? Well, I reckon it's a sort of varying shades of grey. It's going to start in the top left-hand corner, pretty dark. It's going to get lighter as it goes across 5, 6, and 7. As we come down here, it's going to get lighter. So that is maybe 16 shades of grey, unlike the book where there's 50 shades of grey. Of course, it's going to be much more exciting because you today are going to see 256 shades of grey. I've never read the book, so I don't know what it's about. Right. The first step in enhancement, 1. Obtain the image histogram. And the image histogram is a graph of the distribution of pixels. It is going to look something like this. It is going to be a graph of the number of pixels against the grey level, intensity. And let's scale this up. Let's have up to 4 values. That should be enough for this image. 4, 3, 2, 1, and 0. Now, as a suggestion for the intensity, don't start the intensity on the left-hand side of the horizontal axis, because chances are in an image you may well get pixels at that intensity, and you will be drawing them on the axis, and it might be a little bit confusing. So offset the 0 on the intensity away from the vertical axis. So let's call that point there 0. And for the intensity for 4 bits, we're going to have how many greys? How many values? 16. 0 is the first value. It will be 0 to 15. So let's 1, 2, 3, 4. And I think that's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's the axis obtained. Right. How many pixels are at 0 in the image? 1, 2, 3. 1 pixel at 3. Yes? Intensity 3, we have 1 pixel. 4, 3. You keep telling me, save me looking up. 5, 4, 6, 3, 4, 3 or 4? 4. 7, 2, 8, 1, 9, 10, 0. Okay, that's the image histogram, the distribution of pixel values. Now, if you integrate or add up the histograms, you should get the resolution of the image. So there's a check. I've got 16 pixels. This is my histogram to make sure I've covered them all. 1 and 3 is 4, 8, 12, 14, 15, 16. So it looks as if the histogram is complete. Now that's a tiny histogram for a tiny image. Real images, the histogram, the horizontal axis will be 16 million. It will be a table, in fact. And sometimes the histogram is drawn as a continuous function. No, it isn't. It is discrete populations of each intensity value. So that is your histogram. On that histogram, you can identify 2 important parameters. The minimum grey level, which I will call G min, and the maximum grey level, which I will define as G max. And the operation is to, first of all, intensity shift. And the shift is G min to 0. In other words, I want to shift this histogram down to the left to the 0 intensity. So the darkest intensities in the image, which were 3, now become 0. Right, what is my K for the intensity shift algorithm? I want to shift it from 3 to 0. We've got a visiting professor from Caltech with us this morning. Did she know the answer? No, gosh. Okay, you can be better than Caltech. Come on, guys. 3 goes to 0. K equals, obvious, minus 3. Wakey, wakey. K equals minus 3. Now, what that will do is that will shift the histogram to the dark region of the spectrum, with the darkest pixel in the original image becoming absolute black. So let's draw the shifted histogram. So it is going to be one, 2, 3, and 4. And this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I've got right. Now, that was the histogram we had. There it is. We are shifting it left by 3 places. And if I don't make a mistake, I think we are going to get, where's my red pen? We are going to get 1 at 0. We're going to get 3 at 1. We are going to get 4 at 2. We are going to get 4 at 3. We are going to get 2 at 4. We are going to get 1 at 5. And we're going to get 1 at 6. So that is the shifted histogram. Get rid of that one. Now that is 0. What is the value of the maximum pixel in this histogram now? 6. But what is it in general terms?
7.
Now, don't give me a number. Give me a function of the G's, G max and G min. The maximum pixel was G max. I've subtracted G min from it. So what does it become? G max minus G min. Gosh, he knew that and he wasn't even here. So we can now identify this point as G max minus G min. Right. What shall we do now? Let's intensity multiply. And we want to intensity multiply so that the brightest pixel now becomes maximum white. Now, the reason we've shifted to 0, first of all, is a subsequent multiplication will not change the value of the darkest pixel. It's 0. You can multiply it by what you like, it'll still be 0. So we're anchoring the histogram now at the black end. But we want this point, in general it's G max minus G min, to go to white, and white is 15. So can anybody suggest what the multiplication constant K is going to be? G max minus G min, and I want it to become W.
$15 over 6.
Now, general terms. W
over G.
divided by G max minus G min. And what will that do? It will not change the blackest pixel at all. It will not change the first pixel. A little bit, it'll move up. But as we go up gradually, and this point will be moved to there. So if we now look at the actual values on this particular histogram, W is 15. G max was on the original histogram 789. G min on the original histogram was 3. So the multiplication is going to, the factor is going to be 15 over 9 minus 3, which I hope you can do the arithmetic for in your head. It is 15 divided by 6. And I think when I was doing mental arithmetic, it was equal to 2.5. Yes? So let's now do the multiply on the histogram of the image we're playing around with. And we've got the intensity number and intensity. 1, 2, 3, 4. And the intensity is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right. 2.5 times 1. Times 0. 0. At 0 we have 1 pixel. 2.5 times intensity 1. 2.5. 2.5 doesn't exist in a fixed point representation which you have at grade level. It's got to be integer. 2.5, shall we round it up or shall we round it down? Your choice. If it's an exam that's 39.5, shall I round it up to 40 and you pass, or shall I round it down to 39 and you fail? Up. Okay, so that would be integer of 2.5 will be 3. So this population of 3 pixels goes now to intensity 3, which will be there. There. The next intensity is 4. Multiplied by the multiplication factor 2.5. 2.5 times 4 is 10. So that is going to, we're doing this right, aren't I? 15 divided by 6. No, the second one is intensity there is, let's write them down, 1, 2. I thought it was getting big. So the intensity there is 2. 2 times 2.5 is 5, so that will go to 5. So we now have an intensity of 4 at, a 4 population at intensity 5. Now the next one here, I hadn't done this very carefully. The next one is 3. 3 times 2.5, 7.5. You want 8? So that will go to 8, and we will have another 4 at 8. And then we've got 2 pixels at 4. 4 times 2.5 is 10, so those will go to intensity 10. So that will be 4 there, 2 there. And we've got 1 at intensity 5. Intensity 5 times 2.5 is 12.5. Do you want it to be 12 or 13? Go for 13. There is some approximation you can see through the roundup. So that one goes to 13. There's 2 there. And if we've got everything right, the brightest pixel in the shifted histogram was G max minus G min. We are multiplying by W minus, divided by G max minus G min. So the G's should cancel out and we should get W if we're lucky. Right, it was intensity 6. 6 times 2.5 is 15. So that will go to intensity 15, and there will be, oh, there should be 1, sorry, mistake there. That is 1, and that will go to 1. We now, ladies and gentlemen, have a histogram that covers the full grayscale range available to us. The image should look better, but all we've got now is a histogram. So the poor security guards with a histogram, you give them that, so that's the enhanced image. He or she won't make any common sense of it. So we've now got one vital step. We've got to get back to an image. And getting back to the image, we need the pixel update table. And this is a table of all the possible pixel values on the input image before we start enhancing, and the values they will take in the new output image. So if I just label it input pixel, just put input PIXL, and the output. So immediately, like the truth table, you know the input pixel values, and they are going to be 0 to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right, the output pixel. We've now got to compare the original histogram with the enhanced histogram. In fact, I can show them all 3 there. That's good. Right. We don't have any pixels below 3, so there will be no update. Go away. There will be no update on 0, 1, and 2 because they don't exist in the original image. Pixel 3 comes along. There's one of them. After processing, shifting, and adding, that pixel there has become that pixel there, and its intensity value is 0. So the update pixel, all the pixels 3 in the image become 0. The pixels which had original intensity of 4, and there was 3 of them, they become this entry in the final histogram, and they will be intensity 3. They've got a bit darker. So 4 goes to 3. 5, these pixels become this one here. They will go to 5. They don't change. It can happen. The pixels at value 6, they are now going to go to pixel value 8. Pixels at intensity 7 are now going to go to 10. Pixels originally at 8 go to 13. And pixels which were the brightest in the original image, which were 9, will now go to 15. And of course, the other ones don't occur, so we don't need them for the update. So that is your update table. So you've now got to update the image. Where was the original image? Let's go back to it. There it is. A clean sheet of paper. Oh, this is so much better than writing on these white screens. Right, there's the original image. There's my update table. The output image, the answer were this an exam question, is 4 by 4. And what you do, find all the pixels in the original image that were 3. There's one of them. What is the update value? The update value is 0. 3 in the original becomes 0 in the enhanced image. Now the 4s, 1, 2, 3 of them, the 4s become 3s. The 5s, 3 of them, the 5s don't change. The 6s become 8s. The 7s become 10s. The 8s become 13. And the 9s become 15. And I've got some gaps I've missed out. I missed out a 5 there, and the 5 doesn't change. And the 6 there I've missed out, and the 6 becomes an 8. And that is the enhanced image. And even with that low resolution, you should realize it's a better image to see, because it has the same graduation of dark to light, but it's more enhanced. The darker regions are much darker. Maybe the 5s haven't been changed, but the brighter regions have got much brighter, up to 15 maximum white. And that is effectively now using the full grey level range to display the image. So you're spreading out the information from the image which had a constrained original histogram. So that is image enhancement. I've got 5 minutes left before we have a break. So that is what has happened to my original image. Let's go back to it. And of course, you'd never do this image enhancement using pencil and paper, except in an exam. And you'd never do it to 4 by 4 images, you'd be doing megapixel images. So it's got to be a computer-based method. So that's what's happened with those 2 images. Or is it? Do you think if it's a 512, 8-bit resolution, I'd applied the original algorithm to those images, would I have got that output? No, something has been lost. We can see in the original images, it looks a bit like a computer screen in there. That has disappeared. We have actually lost information in the bright region. And what is happening there is not simple enhancement, it is localized, bandpass enhancement, if you like. And what we're saying there is we're looking for the person, we're not interested in the details in the bright region. We will sacrifice the information in the white region and lose it because it will white out, because remember our algorithms lock at the maximum. So we've lost information in the white region. What we have gained is a spreading of the darker region. And that is known as selective enhancement. And that is in fact what you would do if you were using one of these for real. In fact, you'd have interactive Gmax and Gmin which you could control, and you'd be looking there to get the best human perceived image to see what was going on. So the next step is to look at selective normalization. And I think we'll have a 10-minute break now, and we'll start that in 10 minutes. Any questions? Get on top of this method because it's a nice, interesting little topic to set exam questions on. That piece of dirt in my eye irritates me. And another faux pas. If I were to set an exam question on an image enhancement, I guarantee a third of you would give me the answer, the enhanced histogram. You've got to take the final step. You've got to take the enhanced histogram back to an image. So again, that is an intermediate step, and that pixel update table. In fact, we go back to the pixel update table. In the real world, you needn't bother with the pixels that don't exist on the input image. I could have just written down, what was it, 4 to 9, because the rest of the image, the pixel values don't occur. Now, there's another problem we're going to see in real life, which we've got to deal with, is in a simple example like that, it's quite possible you don't get any black or any white pixels. But on your brand new iPhone 13, which you've all got, I guess, or 13 the latest, or 14 now, you've been sold a pup with that phone, because I can guarantee you that some of the pixels on the screen, some of the CCD cells don't work. You've got 16 million of them. 100 might be faulty. And faults that occur, remember Ian's fault system, stuck at, they're likely to be stuck at maximum or stuck at minimum. So with a real high resolution image, with the very first histogram, where was it? He disappeared. Lost enough. No, I should label my. Anyway, but the very first histogram went from 3 to 7 intensity range. You will, on that very first histogram, find some pixels in a real image, a megapixel image. Some pixels will be G min is black because they're faulty, and others will be G max is white because they're faulty. So in a real situation, you can't take the absolute minimum G min or the absolute max because there will be noise problems and faulty problems. So you might look at the histogram. If I draw it as an analog function, if the histogram is something like this, the sensible estimate, and again it's an estimate, it's not a guarantee, the sensible thing would don't take that as G min, take that as G min. And maybe take, if that cuts down there, maybe take that as G max. Because if you take the limits as the initial starting point, you can't do anything, because it's covering the whole of the spectrum. Okay, we will have a break now, it's 5:02, and I'll then look at band pass or local enhancement. Any questions? I told you it would get easy, didn't I? Doing your project at the same time, are you?
I was just like actually. I was going to show it fell off my desk because I went to go reach over to get the new batteries, and then I put it to the so I just like I was like standing up with your headphones, and I was like, oh, that's an other bit actually both of it. It's actually that bit is still works. Yeah, but I mean, look, I left it out like this, so I can just plug it in. I mean, it even still works because then you can try it. I don't find it.
How many have we got online? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16, 18, 20, 22, 24. Only half the people registered are here.
Oh, right, no, I'm using the program.
Zero, if you got zero, actually tell them the numerical value 0.
I understand.
15 is black. Now the real image, with 8 bits resolution, absolute black.
Oh, no.
0 again.
It's fine.
Absolute black.
Be back in 2 minutes.
All different.
And on the whole license, Instagram,
Yes.
which one do we?
You've got the shifted to 0, which is that one. You now want to in fact spread that across the whole speculation. So the multiply won't change the bottom at all, gradually changing more and more. So it will take us proportions of it. So you multiply by K, W, which is in our case 15. Its real image it will be 2 times 5. Divided by this value here, which is the maximum in the shifted algorithm, which was G max minus G min. We want that to go to W, so it is W divided by G max minus G min.
And the number of pixels is missing even after you.
Oh yes, because it's the original image. The number of pixels comes from that. Silence. How are our projects coming on? It's February now, you've got another month left to do your project. You should be thinking about writing it up now. Certainly the introduction, the review. Anybody not started their project yet? God dear, if you haven't, you have to bribe Dr. Beer with large sums of money. I say it's been recorded. Joke, everybody. Just an encouragement for students to get on with it. This is not man-machine control, is it? You have to think about it.
I was going to show a lecture yesterday, but then it fell off my desk because I went to reach over to get batteries, but I forgot it was still attached to my arm, and it just went everywhere, and now it's not wanting to listen at all.
Yeah. It would be actually better, instead of using those stick-ons, if you cut your elbow off and put some probes directly into the nerves. That would be much better contact then. Work much better. Yeah, it's all electrical signals. You move, you feel the tendons move in your forearm. There's no movement there. The signals down to the muscles are electrical. Electrical to muscles. Why not have electrical from the arms to prosthesis? And then with prosthesis, there's a very interesting problem called phantom pain. If you are unfortunate enough to lose an arm or a limb, every so often that limb which isn't there will itch, and you want to scratch it, and you can't because it isn't there. But if you have a computer-generated your arm with a prosthesis on or a picture of it, and you can actually scratch the image, somehow the brain thinks you're scratching the actual pain, and it goes. Talk to Dr. Musavi about that. He's done some research on it. Yeah. You need some visual cue that you are scratching what's itching. And if isn't there a picture of it, can suffice. This is my 4th week of lecturing, you your 5th. Who's supervising this?
This is just
You don't think, is it?
Yeah, just an extra thing size.
Yes, 0 goes, no, 0 is on the multi. That's the shift.
No, this is the shift. That's the next one.
No, that's the original histogram. No, that's the original histogram. That is the shift to 0, and then that should be the multiply. That was the original histogram. That was the shift to 0. This is the multiply. And yeah, you should have anything more there, but wrong there. Because that doesn't move on a multiply. No. It's the intensity of multiply, not the intensity. So that should go over there. 1 becomes 1 times 3.5, we round up to 3. So that intensity goes there. The 4 there goes to the 5. Yes, that one goes to there, and that is covering north. Maximum black.
And then you've got the update.
Okay, 5 past, shall we start again? Right, selective enhancement. We are not going to enhance the whole image. We are looking at or wanting detailed information from a particular sub-band of the intensities. Usually it's the dark region, but in the case of my example here, where's it gone? In the case of example here, I want to find the guy, but if I wanted to see what was on his computer screen, I might not be interested in the black region. I might be interested in enhancing the brighter region. So it can be either end of the spectrum. Let's take the original histogram, which you already have. So I now, in this enhancement, I want to look at the darkest region. So let's take the darkest half of the image. Okay, it's very low resolution, so it seems trivial, but when you're dealing with megapixel images, it's more sensible. So if I were to take that intensity, the G min would be the same. And there's 16 pixels if I want to enhance the darkest 50%. Let's see how far we get up the intensity scale with 8 pixels. There's 1 at 3, there's 3 at 4, and there's 4 at 5. So this point here would be G, let's call it G 50%. So that is the range. It's quite a small range of the darkest 50% of the image. So what we're going to do is use exactly the same process, but instead of taking G max, we're going to take G 50%. So above G 50%, pixels go to white. So we only follow the bottom half of the histogram. And if I were now to do a shift, and the shift is going to be K equals -3, and this is for the bottom 50%. We're going to get one, 2, 3, 4. This is the number. This is the intensity. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right, K is -3. The 1 at 3 becomes a 1 at 0. The 4 becomes a intensity at 1. No, 3 isn't 3. Becomes an intensity at 1. And the 4 at 5 becomes an intensity at 3. And that is the bottom half of the histogram shift. So we're ignoring the top half. We now need a multiply. And this is going to be G 50% minus K, which in our case is going to be 5. Right, so, and the intensity multiplier is going to be 15 minus G 50% was, what was it now? In fact, it's going to be divided by 2, isn't it? So, the multiply. 1, 2, 3, 4. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 1 at 0 remains a 1 at 0. The 1 at 1 multiplying by 15 over 2, 7.5 goes to 7.5. You ought to be 7 or 8. Doesn't matter, just be a slight change in the shade of grey. All shades of grey are interesting, they tell me. Oh, you are sleepy this morning. Let's take it to 8. So this 3 will go to 8. There it is. Let's put a straight line. And the 4 goes to 15. Same principle, even more sparse, barely sensible, but it gets the idea of what we're doing. We're just taking the bottom half of the histogram and come in. No, all right. So that's your enhanced histogram from the darkest region. What do we need now? Pixel update table. Pixel update table. And the values we need to go back to the original histogram. And the original histogram was that one. We were taking the 50%, so that was G 50%. So the pixel values are simply going to be 3, 4, and 5. No need to write all 15. And from that, the output histogram, the one that has been enhanced, we find that 3, which was in the original histogram there, that 3 goes to there in the shift and goes to there in the multiply. It goes to 0. The 4 after shift is 1, after multiply it becomes 8. And the 5 after shift becomes 2, after multiply becomes 15. Right. Pretty trivial. Output. Let's go to the original image, and the original image is somewhere here. There it is. There is the original image. So I want to go from here to here, and this is the update. The 3 is a 0. It's only 3. The 4s become 8. The 5s become 15. What do the 6s, 7s, 8s, 9s, and the rest of them become? Black? You want them to go black? Try the exact opposite. 15, white. So, you get white out in that top region of the image, the brightest part we're not interested in. You're sacrificing that to see what's going on in the darker region. And with a stretch of the imagination, at this very low resolution, you should be able to just imagine that originally this was a fairly dark grey area. It's going from 3 to 5, pretty dark values. In the enhanced image, it's getting brighter and brighter and brighter. We're seeing much more detail there, but we've lost the white region. And that is exactly what has happened in that image. We've started off, we're interested in this region here, we've expanded that, but we have sacrificed the information which was originally in the white region of the image. Of course, you could have done the other way around. You could have expanded the white region, in which case this guy would completely disappear. He would black out, and we could have expanded what's going on there. Right, so that is image enhancement. Its practical implementation is obvious. People are looking at you all the time and monitoring you with CCTV, and they want to see the best view. What you would have in a practical system is an interactive system. You would have a camera capturing an image. You would have two controls. They would be variables, and they would be Gmax and Gmin. And you could have a user control on those. You could get a Gmax and a Gmin, and the system would enhance the image for those parameters. And it will take a few seconds because on real live images, you're dealing with 16 million operations. It can be quite slow. You've got to have fast computers to do it. As I said, a PC 20 years ago wouldn't even touch it in real time. And so that would be what's going on if you want a really boring job, or might be interesting what you're watching. With monitoring these, you sit in the office with the two controls, Gmax and Gmin, tweaking them and saying, oh, yes, that's getting better. It's a bit like a learning process of the human. They are changing the Gmax and the Gmin to improve the visual appearance of the image. That's the sort of process we had in neural network learning. So that is two very simple monadic operators, shift and multiply, and we've used them to do quite an important job, which is enhancing images. So that's pretty good. Any questions? Okay, in your own time, to prove to yourself, you don't have to prove it to me, but you can do it. Take a random image. Take another example of that in your own time. Make sure you've got values which don't go below, say, 2 or 3, don't go above 12, because then you can't, if you've got values at maximum initially, you can't get anywhere. Get your own image, enhance the whole image, and then do a selective enhancement, just to make sure that you understand what's going on. These are easy concepts. You've seen them before. At 8 o'clock this morning at breakfast, you'd never heard of them, and it was impossible. So you've gained some information now, and you never know where they might pop up again. Right. That was monadic operators. What else do you think there is? We're operating on 1 pixel. What might be another interesting thing to do? Functions of 1 pixel. When you're a research student and do something new. What if we did operations on 2 pixels? And what if they are coming from different images? These don't lead to such interesting image processing techniques, but they are used in graphics and entertainment and special effects. So it's worth you knowing what they are. So the next topic is dyadic operators. Two pixel operator. Again, some books will say dyadic, which I think is a Latin name for 2. But in the exam, should they come up, I would say 2 pixel operators. Because I don't want you to be stumbling on the language. So 2 pixel operators. What is the idea here? The idea is we have 2 input images. A and B. We extract a pixel from A, call it AIJ, and we extract a pixel from the second image B. And the key thing is it's the same coordinates. It's the pixels in the same position. AIJ, BIJ. So for the whole image, we would start scanning the image, starting at the origin, which is top left in images, going across AIJ, BIJ. They go into a process. And this is a function of Aij, Bij, function of the two inputs, one from each image. And the output goes to a third, the output image, which I'll call C. And it goes to exactly the same position, Cij. Now, some operators will see later on, we will be putting pixels in different positions of the output. But at the moment, the same location on both inputs and the output. And again, it has to be done for every pixel in the image system. So, the first operator with dyadic operators is image add. Sounds like a simple operation, simple arithmetic. So the output image is Cij equals Aij plus Bij. You might think that is adding 2 pixels, but there's a problem. We have fixed resolution for cells, 8 bits in real life, 4 bits in exam questions. What is the minimum value of Cij? What is the lowest value Cij can be? 0. Now, if the maximum individual pixel values are W, white, what is the maximum value of Cij?
30.
W the individuals. Yeah.
W's?
W, 2W.
Yeah.
It would be 31 actually, on the right idea. Right, so this is going to take us out of range. So we have to apply a correction factor to that addition, which you don't do in normal arithmetic. The correction factor, so obviously, a 5-year-old can tell me what the correction factor is. What is the correction factor?
Divided by 2.
Well, spot on, my friend, spot on. Divide by 2. Why? Max Cij is 2W, but must be in range 0 to W. Right, so that is the image add. Let's move on. If we've got image add, guess what? There's image subtract. And image subtract, Cij equals Aij minus Bij. That's the starting point, but we've got again a problem because of the fixed point arithmetic we're using. Cij is going to be an image, an output image. It's got to be within the range of 0 to W. Now, using the minimum value of the image pixel as 0 and the maximum value as W, what is the minimum value of Cij?
Minus W?
Minus W. And what is the maximum value of Cij? W. So we now have a range of minus W to plus W. And we've got to bring that in the range 0 to W. Otherwise we will lose half the image. So the correction factor, if it's minus W to plus W, if I add W to it, the range is going to be what? 0 to 2W, because I want it 0 to W, divided by 2. And so that is a correction factor for subtraction, which is a form of inverting an image. So, image max. Again, these are special effects, these are obvious ones. Image max, we are taking the maximum pixel from each of the images. We're sort of superimposing them in the upper end of the intensity spectrum. So, the image max is going to be Cij equals Aij, for Aij is greater than Bij, and it's going to be Bij for Bij greater than Aij. That's really for special effects. We don't really use that in serious image processing, scientific image processing. What if Aij and Bij are the same? You've got to arbitrarily apportion that to one or other class. So it could be greater than or equal for that one. It could be the other one. You will find in image processing, there's not a single answer. There are approximations to the resolution. There's effects which are imperceivable. That has to be applied to keep the algorithms working. So if there's image max, so this is getting simple, I'm insulting you, there's image min, isn't there? And image min is the opposite of image max. Cij equals Bij, Aij for Aij is less than Bij, and Bij for Bij is less than Aij, and put the equals one there. Okay, I'll pass over those quickly. They're special effects, you know what they are, they're relatively simple. The only thing you might get wrong is the correction factors. Remember, got to be in range of 0 to W. Right, passing on now, getting on to something more interesting. Window operators. So far, we've been using 1 pixel per image, 2 pixels per image. This is more than 2 pixels, and it's often referred to as a window operator, and the block diagram for it is an image, and the image is A, and we will take a window, normally, but not necessarily, a 3 by 3 square. And that is providing 9 bits of information to my function. The center pixel of the window for the A image is Aij. And that will produce a pixel of an output image. Let's call it C, and that is going to the physical position of the center of the window. Right. This is going to lead us to filtering operations, edge detection operations. They are all window operators. Right. So the first window operator I want to look at is low pass filtering. and this is often referred to as smoothing. And this is where you are taking an image, you are in fact reducing the contrast, you are blurring it, you are smoothing it, which can be a good thing because it reduces variability if you're capturing images that go into a neural network. You want things not to change too much in the real world. So you can pick out constant features and things that are relevant to the classification. So, the window operator for a low-pass filter is extremely simple. The 3x3 window, it has coordinates, and the coordinates are, does anybody know? It can't get any simpler than all 1. And that correlates with the image. And if we regard this as W and the part of the image as I, which it is operating on, if that is pattern I, the operation you are calculating is W dot I, which is the summation Wi, which is exactly the same as you're doing in a mechanical bit neuron. But instead of you having to work out the weights to do the job, I'm giving you the weights, and the weights are all 1. Right. Let's have an example. Now, exams. Should a filter image be going on the exam? You should expect 5x5 images. Why? Because the window operator is a square. If I were to put this operator on the top left-hand corner of the beginning, because the output corresponds to the center of the window, you are losing the top line in the output. The dimensionality will be reduced because the pixel is the pixel corresponding to the position of the center. So in applying this, we are losing the top row, the bottom row, and the 2 columns, which is absolutely trivial at 4,000 by 4,000 resolution. You would not see it in standard images. But in simple examples, the smallest resolution I can have is 5x5. And a 5x5 input image will give an output image of what dimensions? We're losing columns, the edges basically. 3x3. And if I went down to 3x3 examples, it would be so trivial, the output image would be just a pixel. And that is too simple. Right, so let's take a filtering example. And let's take an image . And let's assume it's been enhanced, so let's keep it simple. All black on the top row. Again, you can make your own examples. You don't have to copy this one down exactly. 12, 0, 0, 0, 15, 15, 2, 15, 15, 15, 15, and the bottom is going to be all 15s. Right, what does that image look like for you, a human? What's the appearance of that image? It's a black triangle there, followed by a white triangle with a little bit of grey in the middle. So the actual image looks something like this. If it was an analog image, it would be a bit of noise there, something like that. We want to filter it. We want to low-pass filter it, smooth it, so the edge will be less sharp in the output image. Right, the window, actually I can use one of this to do it. Is all ones. In fact, let me see if I can do it this way. Those are the weights written in red. So there's the window, and it goes on the image, and it goes to the first position. We are in fact adding up the coefficient of the filter window with the pixel value of the image. And of course, all the images are naught. So if we take the output down here, right, all noughts, it is going to be naught. You move the window over to the next position. What is the correlation of that window with the image? 15, good. And move it over to the third position. What's the correlation there? 50? No. 42. 1 times naught plus 1 times naught plus 1 times naught, 1 times 12, naught, 15, 30, 42. Yes? Start scanning the second row. And that is going to be 42. In fact, is it better I just have a plain window without the weights in, because they're so obvious that they're one? There is the window we're looking at. 32, I think. Yes? 32. Move the window over there. What's it going to be? 60. There. 60, 75, 85, 87. Move it across down there. That is going to be 60, 75, 77. Yes. Move it across there. That is going to be 15 times 30, 60, 90, 105. And that is going to be 30, 60, 90, 120. So that is the image. It has been low pass filtered, and we get that output. Now, if you try to display that on a image system, there is only 2 pixels that would give the true value, which would be 0 and 15. All the rest would be above the maximum, and then it would be white out. You'd get no sensible image at all. What's going on? Okay, go back to the window there. What is the minimum value from the image I can get correlating it with that window? That window sits on the image. What is the minimum possible output that can occur? 0. Right, now what's the maximum possible output that can occur? 135, 9W.
Yeah.
9W. So in doing this filtering, we have gone from a 0 to W input range to a 0 to 9W output range. We need a correction factor. What is the correction factor? Divide by 9. So having got that, it is absolutely essential we divide by 9. So in doing that, let's leave that up there. In doing that, and it is going to be naught divided by 9 is obviously naught. 15 divided by 9, it's got to be integer. What do you suggest? 2, I think. Yes? (42) divided by 9. Integer. 5. 32 divided by 9. 4. Thank you. 60 divided by 9. 7. 87 divided by 9. 10. Well, 77 divided by 9. 9. 105 divided by 9, gosh. 12, thank you. And 120 divided by 9. You've got a calculator, haven't you? 14. So that would be the low pass or smooth image. Now that output will only correspond to the center of the input image. So when we're making comparisons, oh, these damn pens. When we're making comparisons visually, we can only take the 3x3 center of the image. If it were a real image of thousands of megapixel image, you wouldn't notice it. But now if you can compare the blue outline section there, that is clearly a black-white image. The dots are absolute black, the 15s are absolute white. So that's a clear, sharp image. We have smoothed it, and what we have got there is, yes, the top left-hand pixel is black. We've got some greyish ones, 2 and 4, which are dark grey. We're getting a bit lighter grey, even more lighter grey with the 1012, and the whitest would be 14. It has smoothed the image. Yes?
Does that reduce the quality?
It reduces the quality of the image, but it changes the variation. It reduces the variation. And what we want to do in pattern recognition, the real world is hugely variable. If we can reduce the variability, we might detect the images better. Now, if it's a television program and you were enhancing or broadcasting it, the very thing you would not do would be to low pass filter the image. Because it does blur, it does, unless of course to remove certain parts of the image, which happens. Which is also very interesting because when you get these pixelated images on pictures, if you squeeze your eyes and blur the images so that you are reducing the sharpness, the chunkiness of the image, you can sometimes perceive more detail. You can sometimes get sub-pixel information, which is quite interesting. That's your brain working. Okay, we've covered a lot of material. We've got to 6 minutes to go before our time's up. We've covered a lot of material this morning. Any questions?
We divide by 9 because it's because of
We divide by, well, you tell me why we divide by 9. There is the window. It's correlating with an image. An image can have pixels of any value, in the case of exam questions, between 0 and 15, 4 bits. In case of real images, 0 and 255. The maximum part of the image that window could set on was where all the images are white. If it's looking at this board here, all the pixels would be white. That would be 9 white at the output. If it was looking on this region here, all the pixels would be black. That would be 0. So the maximum range of the correlation of that window with an image is 9W. And what we're getting here is all the values in between. We're getting an absolute black. We haven't got an absolute white there, but that's the whitest it can be. And it's giving me values between 0 and 120. That requires much more than 8 bits resolution to display those numbers. So to bring it into range, divide by 9, the blacks won't change, the 9 W's will come to W, and everything in between 0 and W will come back to within range 0 to W. Yes?
You know the window, is it normally the same number always, or is it like very?
The coefficients for a low-pass filter are always 1. Another way of interpreting the low-pass filter is averaging. Now, if you knew nothing about filtering, if I told you to average the value of the pixels in that window, you would add them all up and you would divide by 9, which is precisely what the low-pass filter is doing. The weights are 1, which means you add the numbers, and the average is divided by 9, because there's 9. So it really makes common sense.
If the window was 12, total would be 12 then.
If the pattern window,
Yeah.
if the pattern window was 12 by 12, then the output image would be 10 by 10. Because you will always lose the borders. Because if that window is sitting on an image, the best it can do, I've written on that now, the best it can do is be in that position. And the output pixel will be that pixel. As the output pixel, go back to the original block diagram, the output pixel is at the same location as the center of the input window. And the input window doesn't have to be a 3 by 3. It could be a 5 by 5, which is averaging over a bigger area. And that would be the same effect if I had a 5 by 5 window with all ones. It would be the same effect as using the 3 by 3 window 3 times. So bigger windows can occur. There's no real advantage. You can get the same effect by filtering and then filtering again. So, okay. So let's recap. The monadics. The main things are image add and image multiply. You must make sure the output was in the range 0 to W. If you take an image and you want to enhance it, you need the image histogram. The image histogram is a graphically table in a computer for big systems. It is a table of the intensity values and the number of pixels across the whole image that have that intensity value. So you take an image, you find how many pixels at 0. That goes into your histogram. How many pixels are in intensity 1? Right the way through to absolute white. When you've got that, you can identify the minimum intensity value, which I call G min, the maximum, which I call G max. Then to enhance an image, you take the image, you get the histogram, you shift the histogram from the darkest pixels, G min, to 0, which is done with a intensity shift with a coefficient K, which is minus G min. G min is a value, you want G min to go to 0, you have to subtract G min. It's common sense. That brings the maximum pixel value G max down to G max minus G min. You've then got an intermediate histogram. You then need an intensity multiply. And that is going to be W, the maximum brightness, divided by the maximum value in the shifted histogram, which will be G max minus G min. So the multiply factor is W divided by G max minus G min. And that will then give you the histogram, which has the darkest pixels at black, the brightest pixels at white, absolute white, and everything spaced out in between. Then don't sit on your backsides and think the job is done, because having got that, you've then got to get back to the image. And what you do then is you take the original histogram, pixels at the lowest value, you trace those pixels through to the final histogram, the normalized histogram, and find out what the intensity value is. So the lowest pixels, I think an example were intensity 3, we traced them through, they became intensity 0. So you then have a pixel update table of all the possible input values, pixel values, and what they will be in the enhanced. And you scan through the original image, reading the pixel value, go to the pixel update table. It was 3, it becomes 0, replace it with 0. It was 5, it becomes 2, replace it with 2. And you scan the image pixel by pixel, and you've got your enhanced image. Good stuff. Okay, it's 5-2, time's up. Well, what immaculate timing? Yeah.
Enjoyable? Better than online?
In the computer program, you start to see them.
I was wondering, how many of you got the job for?
Go through the image. How many pixels are 1?
Anyone got job for first?
How many pixels are 4? 1, 2, 3.
No, almost yet.
How many pixels are 5?
Well, I said some people already got the job, but I was wondering if anyone got it.
Is that the record of the computer?
Not yet, I'm thinking about it. So,
That's okay. Ask your visiting professor from Caltech.
well, that will be.